Our today's lesson is going to be on discrete exponential functions. An exponential function is a function whose output values have a constant ratio for each unit of increase in the input values. An exponential function is denoted by f of x equals a b to the x power, where x is a real number. A cannot be equal to 0, b must be greater than 0, and cannot be equal to 1. The constant ratio is the base b. Let's compare and contrast a linear discrete function to a discrete exponential function. Now, I have written in yellow a linear discrete function. Remember, it usually comes in the form of y equals mx plus b. And we're comparing that to a discrete function. All right. If you notice on the left, this just has an increase of 10 in each of these values. And if you look at the other table, notice that they increase by 2. The previous number, you just multiply by 2 and you get the next value. And in general, when you graph a linear function, it's always going to form a line. So when you graph this, you're going to see this. Whereas when we graph a exponential function, it's going to increase rapidly, so it's going to form a curve like this in general. All right, complete the table for f of x equals 2 to the x power. So if x is negative 3, you're going to have 2 to the negative third power, which we know is the same as 1 over 2 to the third, which is 1/8. And 1/8 is approximately 0.125. And so on. If I have 2 to the negative 2, that's 1 over 2 to the second. You got to use the rule of exponents here, which is the same as 1/4. Or I can write 0.25. Or if I have 2 to the negative 1, that's the same thing as 1/2. That's the same as 0.5. 2 to the 0, remember any exponent raised to the 0 is just 1. So this is going to be 1. 2 to the first power we know is 2. 2 squared we know is 4. And 2 to the third is 8. And what we want to do is graph that to see what we get. So if we're going to graph f of x equals 2 to the x, remember when x is 0, we get y is 1. And when x is 1, we get 2. Because 2 to the first power is 2. So it'll be right here. When x is 3, we get 8, because 2 to the third power is 8. So it'll be roughly right there. And when x is negative 1, remember that's going to be like 1/2. So that'd be roughly about there. And it gets smaller. It gets closer to the y-axis as we go, but it doesn't quite touch it. It gets really close. So the graph's going to wind up looking like this. Okay, complete the table for 2 times 3/4 to the x power. Remember the base is 3/4 and their coefficient's 2. So if you were to evaluate that, you would say 2 to the 3/4. If that's raised to the 3rd power. Remember what you would do with this is you can take the reciprocal of this fraction inside the parentheses, so that'd be 4/3 to the 3rd power. And then that'll be 4 times 4 times 4, which is 64. And 3 times 3 is 9, times 3 is 27. And then you just multiply that across. And when you do that, you get roughly this, which you put in decimal form, 4.74. And so on. So you're going to do this with the rest of these values. So you wind up with this. X is 0, that'll be 1, and 1 times 2 is 2, and so on. And notice how the pattern in this, it gets smaller. Okay, if we were to graph this, when x is 0, we get 2. X is 1, we're going to get 1.5. So that's roughly here, 1.5. When x is 2, you're going to get 1.25. It'll be roughly about here, in between there. X is 3. It's going to be a little less than 1, almost 1, but not quite. Negative 1, you're going to get 2.66. So it's a little more than half, but not quite 3. X is negative 2, you're going to get 3.5, so that's like 3.5. So it'll be roughly there. And negative 3, you're going to get 4.74. So it's not quite 5, but it'll be roughly about there. And you see the function coming down like that. It's like a decreasing function there. All right, the height of a drop ball is an exponential function of the number of bounces. On its first bounce, the ball reached a height of 15 inches. On its second bounce, the ball reached a height of 7.5 inches. Write an equation for the height of the ball as a function of the number of bounces. All right. So in order to do that, we know the general. Let's write a good variable first, though. We know h. That could represent the height of the ball. And we know n, let's say that represents the number of bounces. So in general, we want to find this. We're going to write this as a function, the height is a function of the number of bounces. And we know the general form is a b to the raised to the n to the number of bounces. And what we're going to do is going to find out what b and a are. So let's do that. First of all, we're given that the second bounce was 7.5. And if I divide that by 15, that tells us the first bounce. That's going to give us the value of our constant. If you simplify that, that's going to give you 0.5. And what we can do is we can evaluate one of the ordered pairs. We have two ordered pairs from the initial problem. Let's say on the first bounce, it went 15 inches. And on the second bounce, it went 7.5. You can evaluate one of the two. It doesn't matter. Let's say we pick this one. You can get the same result. And evaluate that into the general formula. So let's say h of n is 15. And we're trying to solve for a. And b is going to be 0.5. And let's say we're going for the first bounce. That's what n is. All right, so we know that 0.5 to the first power is 0.5 a, and that equals 15. And what you're going to do is divide both sides by 0.5. So a, our constant, has to be 30. So if you want to write that equation, we can just write it like this. Put 0.5 to the n power. And that will be our, this is the height. That will be our equation. And we can use that to figure out the initial height, or we can figure out how many, the third bounce or the fifth bounce and things like that. For example, what's the initial height of the ball? They didn't tell us that in the problem. What was the initial height when the ball first came off the ground? So, since I have the equation now, I can evaluate that and figure that out. Initial means where it started. So we're going to use n, set that equal to 0 for the initial height. So h of 0 is going to be 30. And then you raise this to the 0 power. Now, according to the laws of exponents, this is 1. So 1 times 30. So the initial height has to be 30 inches. That's what it tells us. So you're going to say the initial height is 30 inches before it hit the first bounce. All right, what was the height for the fifth bounce? Where we're going to use our same equation. And we're going to set n equal to 5 because we want to know the number of the height for the number of bounces for the fifth bounce. So the number of bounces is 5. So we're going to say this to figure out the height. I'm going to raise this to the fifth power. All right, when you do that, you multiply that 0.5 to itself 5 times, you're going to get this number. and you multiply it together, it's going to be roughly about 0.9375. So we're going to say roughly about an inch for the fifth bounce. Just slightly less than an inch, but it'll be roughly about an inch for the fifth bounce. This concludes our lesson for today.